Welcome back everybody to another video lecture by Miss Semino. Today we're going to be talking about chemical formulas. I know it says bonding here, but it's really formulas. And for chemistry honor students, all of this information is contained in your chapter 7. And then for my chemistry 1 students, this video is a combination of chapters 7, 8, and 9. And in class we do kind of combine them together. This first section is also going to be divided into 2 sections. Part 1, we're going to learn how to read and to write formulas. And in the second part, we're also going to learn how to name, or when we're looking at a chemical formula, how to just read the name there. The first thing to know are these chemical formulas, and we've talked about these in class before. So it says here, a chemical formula indicates the elements involved and how many of each type are in the molecule. So for example here, I've rewritten these formulas here because the subscript isn't working so well. So this first formula here is going to be C8H12, and that means that we have carbon, we have 8 carbons, and then we have hydrogen, and then we have 12 hydrogens there. So that's kind of how we read the chemical formula, and we might call it C8H12. On the other side over here, we have aluminum sulfate, and so we have Al, and that's a symbol for aluminum, and then we know that there's 2 aluminums in this molecule. And then we have this, it's called a polyatomic ion here, and we've seen these a little bit before. Polyatomic ion. And so you can see that this one's sulfate, and we know that we have 3 of these polyatomic ions. So this whole thing here, these are sometimes a little complicated to read, is called sulfate. And then this subscript on the outside here is telling us that there's 3 of those polyatomic ions in this particular molecule. So before we get into the next slide, I just want to go ahead and review the octet rule. And remember, atoms are always striving to obtain the noble gas configuration. So remember, the noble gases are found on the right-hand side of the periodic table, and they have full valence shells, and normally that's either going to be 2 electrons they're seeking or 8 in their valence shells. So one of the things that we want to look at first here is potassium, and potassium has 1 valence electron, and I know that because if I look above the column where potassium is, it'll say IA, and this is in Roman numerals, so this tells me that it has 1 valence electron. Now, potassium here is looking to obtain noble gas configuration, so it has 2 options. It can either lose its 1 electron, or it can gain 7 more, and so just looking at it, it's going to be easier for potassium to lose its 1 electron and instead of picking up 7 more. So what ends up happening though when potassium loses this 1 electron is that it has a charge to it. Because right now potassium normally has 19 protons and 19 electrons. And then of course positive 19 plus negative 19 is 0. So normally potassium is neutral. But if potassium ends up losing that 1 electron, okay, it's still going to have 19 protons, but now it's going to have 18 electrons, and it's going to end up with an overall charge of positive 1. So the convention, the way that we would write ion with a positive 1 charge, is we're going to put the K, and then we're going to put the 1 plus. Now, a lot of textbooks or worksheets you might see this written either way, but the general convention is you put the charge and then the sign. Is it a negative? Is it a positive after it? So let's go ahead and take a look at fluorine. Fluorine has 7 valence electrons, and I know again that it has 7 valence electrons because it's a halogen, and above it you're going to see VIIA, and that tells you that it has 7. So again, in order for fluorine to obtain this noble gas configuration of having 8 electrons surrounding it, you can either lose all of its 7 or it can gain just 1 more electron. And again, it's a numbers game, so gaining 1 seems a lot easier than losing 7. So again, normally fluorine would have a neutral charge because it would have 9 protons and 9 electrons. And of course, positive 9 plus negative 9 gives us 0. But in this case now, fluorine, when it gains an electron, so we're going to have 10 electrons now, it's going to have an overall charge of -1. And again, the convention is to write F and then 1 and minus. And this is how we describe the ion here. Now here's just a little table to remind us of some names. We have the cation, and remember, see how all of these have positive charges to them? So remember cats. We like cats. They're so positive. So cations have a positive charge. And then anions, on the other hand, negative. So all of these are going to have a negative charge. And so that's how we generally describe it. Cations have a positive charge, anions have a negative charge. So what ends up happening is that these cations with positive charge combine with these anions, these negative charge, to form compounds that are electrically neutral. And so we would call these cations, calcium is a monatomic ion, barium is a monatomic ion. So mon means one atom. So chlorine, one atom of chlorine is considered a monatomic ion, and more specifically we call it an anion. So on the last slide we saw that we have cations, positively charged ions, and anions combined together to form electrically neutral compounds. So when we talk about electrically neutral, what we're really talking about is that these charges here are going to cancel out and equal 0. So right now, if we were to look at this, I have a positive 2 charge plus a negative 1 charge, and if we do the math on this, this is going to give me a positive 1. This is obviously not equal 0. We want it to be 0 because this will be electrically neutral now. So what we need to do in order to make the compound electrically neutral is let's go ahead and add another chlorine. And so if I go positive 2 plus minus 1 plus minus 1, now we'll finally get our electrically neutral, or 0, as our answer. And so you can see this was already indicated in our chemical formula that it takes 2 chlorines to balance out the charge in 1 calcium. So with our charge here was a minus and then 2 plus. So it takes 2 of these to equal the charge of these, and this is our compound here, calcium chloride. So let's go ahead and look at another compound, or a way that we can put these monatomic ions together to get our electrically neutral compound. So I've got barium here with a 2 plus charge, and then oxygen here with a 2 minus charge. So right away I want to go ahead and look at the charges. Are they equal? They are. So I just need 1 atom of each element to make an electrically neutral compound. So the way that we would write this is BaO. And we don't need more than 1 because we've got a positive 2 and a minus 2, and so positive 2 plus minus 2 is 0, or electrically neutral. So let's do one that's going to be a little bit more challenging. So here I have iron with a 3 plus charge and oxygen with a 2 minus charge. And again, remember, we're going to need to have the oxidation numbers end up to be equal to 0 at the end. So the first thing that I think of is, what is the lowest common denominator, is the word I sometimes use, that I can get to. So in my brain, 3 and 2, well, there's 6. They can both get to 6 pretty easily. So I'm going to look for an overall positive charge of 6 and an overall negative charge of minus 6. So I'm going to do that by adding another iron, so Fe, 3 plus, and then if I add another oxygen, 2 minus, I'm only at 4, negative 4 here. So I'm going to need to add another oxygen to get negative 6. So if we were to add up these charges, you're going to see I have positive 6 here. Then I now have negative 6, and if I add them together, it's going to give me 0 for an electrically neutral compound. So the way that I would write the chemical formula for this one would be Fe2O3, and this is my formula for iron oxide. Well, there is an easier way to write a chemical formula, and it's called the crisscross method, and it's used to write chemical formulas. So the first step, as you can see down here, is we want to list the charges of each ion. We're going to crisscross the number of the charge only. So we're going to bring this number here, down here, and this number here, down here, down to where the subscripts would be. Then you're going to simplify, and we never write the subscript of 1. So here, kind of in step 2, we would have a 1, and then we would have a 2, but again, we don't write this 1 here, so we would leave it blank, so the correct formula is going to be CaCl2. So another way to say that is when you use the crisscross method, you're basically going to take the number of the charge on the cation, and it's going to be the subscript on the anion, and whatever the charge is on the anion is going to turn out to be the subscript on the cation. But again, we don't write the 1, we just assume if we're writing the element symbol there's at least one of them there. A few slides ago, we saw the term monatomic ion, and that meant one atom with a charge. Now we're going to see polyatomic ions, and poly here means many. So we're going to have several atoms put together and that have an overall charge. So a good example here is sulfite. So sulfite is composed of sulfur and 3 oxygen atoms, but overall this is going to have a charge of 2-. So this is how we describe a polyatomic ion, several different elements put together with an overall charge. Some other examples we can see here is we have phosphate, and overall this has a charge of -3. And then we have ammonium here. This is also a polyatomic ion, but notice it can have a positive charge. So polyatomic ions can be positive or they can be negative. And we're going to work with these very similar to how we did with the monatomic ions by looking at the charges and trying to get them to cancel out. So here we have calcium and we have sulfate. So remember, we just simply look at the charges. I have a 2+ charge here, a 2- charge here. So 2+ plus 2- cancels out to give 0 or give us our electrically neutral compound. And so you can see it's just calcium, sulfate. We just needed one of each to make an electrically neutral compound. The next example here is we have barium and we have phosphate here. So now though, this one's not quite as simple because notice we have different charges. We have a 2+ charge and a 3- charge. And so again, my general rule of thumb is think of what the lowest common denominator is. And between 2 and 3 is 6. So it's going to take 3 bariums to have a 6+ charge. And then it'll take 2 phosphates to have a 6- charge. So you can see we took the 3 bariums here with the subscript. Then we have the parentheses, and then we have the subscript of 2 out here, indicating that it took 2 phosphates. So 2 of these polyatomic ions here. Now don't forget, we can also use the simple crisscross method. I want you to think conceptually first, how many of each atom do you need for the charges to cancel out? But also the crisscross method is pretty simple. So if we look here at our ammonium ion, there's really a 1 here even though we don't write it. And so what we're going to do is we're going to put the subscript of 1 by the sulfur here and the subscript of 2 by the ammonium here. And you can see in our chemical formula, it took 2 ammoniums and there's only 1 sulfur, and again we don't write that 1 there. Besides the conceptual example that I gave you on the last slide, you can still use this crisscross method for polyatomic ions. So here we have calcium has a charge of 2+, phosphate, if we're combining calcium 2+, phosphate with a 3-, you simply just take their numbers, you run them down here, run it down here, and then our overall formula for this one is going to be Ca3. Then since I need 2 phosphates, I'm going to use the parentheses, PO4, 2, and here is the correct formula for calcium phosphate. Quick definition here that you should know is when we're talking about empirical formulas, that is the lowest whole number ratio of elements. So if we look here at calcium sulfate, it means that for every 1 calcium ion, there's 1 sulfate ion. Then here we have sodium sulfate, and the way the formula is looking a little weird on the PowerPoint here, but it's Na2, then it would be SO4. So it means for every 2 sodium ions, there's going to be 1 sulfate ion. So this is the lowest whole number ratio of elements, is our empirical formula. So the last thing that I want to discuss before we finish out this first part of the video is the stock system of naming compounds. And we use this stock system by having a Roman numeral match the charge being used. So here we have copper, and copper is a transition metal. And remember that transition metals can be found in the middle of the periodic table, and transition metals can have varying oxidation states. So in our example, we're looking at copper. It can have a +1 charge or it can have a +2 charge. So we want to be specific about which copper ion we're using because it can change the chemical formula as we're going to see. So one way I would do this is write copper 1 and the Roman numeral 1 for the +1 charge, or I'm speaking about copper 2 and then we've got the 2 here, the II for 2 in Roman numerals. So let's just go ahead and look at our example here. We have copper 2+, and then we have nitrate ion. So if we just do the quick crisscross method, you can see that this 2 is going to be here, so giving me 2 nitrates, or this is 1-, so I'm only going to have 1 copper. And the way that we would write out the formula for this is the formula, the name what we would give this is copper 2 nitrate, because it's a copper 2 ion, and then the other ion that combined was the polyatomic ion nitrate. On the other hand, if I have the copper 1 ion in nitrate form, you can see how it has a different chemical formula. So the way that we would write out this using the name is copper 1 nitrate. Okay, well, the next video, you guys, part 2 for this first section, is going to talk about how we write some more of these names for ionic compounds as well as molecular compounds.